Alright, so before we get started with stuff, I will have your test grades up after class today. I have to go back to my office and finish stuff. I just had to meet with Hedvig this morning to discuss grades, make sure we were all on the same page, all our grades are good. So I will tell you just as of now, the average score was about, let's see, 15 out of 22, like 15.4 out of 22 questions, so it's about 70%. So pretty good, but we'll take a look at some of the most frequently missed sorts of topics in class on Thursday. And let's see, anything else before we get going for today? Oh, I know what I wanted to mention. Friday this week, there's no recitation. Just getting caught up, and everybody's going to have the same number of recitations between last test and the upcoming mastery test, I guess. Which is, so we've got this week and next week, and then there's spring break. And then after spring break, there's one more week, and then your mastery test is Thursday the following week. And then like 2 weeks after that's your next regular test. Mastery test isn't like a regular test, and the stuff we're doing between now and then isn't all mastery stuff. There's like two things kind of overlapping. Mastery test is strictly just a computational, like write a formula sort of thing, not really brain power. It's just make sure you memorize these rules. So we're not just going to be spending 4 weeks on that. That's really boring. If you're just spending time on that, it'd be 1 week. But we're kind of building all of this stuff together. I want you to know where all of the things on the mastery test come from, not just how to do them and what they're useful for. So where we left off at the test was talking about how we go from an exact rate function to this summation that represented approximate accumulation due to the rates. And we can make it a really good approximation by making the interval width that we use rates for relatively small. So just this picture up here, I've got a rate function, an approximate rate function used over fairly large intervals, which turns into this approximate accumulation sum, which looks a little bit jagged. But even with that large of an interval width, on this fairly rapidly changing rate function, it's actually not too bad of an approximation overall, especially because this rate function first increases and then decreases. At some points our estimates are underestimates and at some point overestimates. So by the end we're actually quite close to this idea, this true value, this exact accumulation function. So our approximate net accumulation function was this lovely thing. But to get an exact net accumulation, meaning between 2 points or starting from here, how much happens until some other point, whether it's a numerical endpoint, so that'd be a specific value of accumulation, or whether it's a variable endpoint in x, so that I can have a function that describes how much accumulates for any value of x, sub in your own x later. Exact net accumulation function to describe all of the stuff that's going on in there. It's much shorter. It just doesn't tell us where that came from. So the shorter form of this is just to write this expression here, and we're going to write a couple exact accumulation functions in this form today and look at functions that look kind of like that and decide whether or not they meet the criteria for possibly being exact accumulation functions or whether there's something slightly wrong about them. But there's lots of details to this, despite the fact that it doesn't have nearly as many parts in it as the approximate function does. So we don't have to specify a delta x size because, well, there isn't one. We're essentially saying, imagine that delta x is infinitesimally small as you can imagine. So you don't want to assign a number to it because if you did, then you can assign a number half as big or 1,000th as big or whatever. So we're just infinitesimally small. We don't worry about how many intervals there are, just where they start and stop. So this is a function setup, meaning this isn't representative of a value. This is a whole function that measures accumulation starting at lowercase a, just like before, and going on through any x you want. You can substitute in a value of x later. So if I wanted a sub f of 3, this would be a 3 at the top here. And that would tell me the accumulation between lowercase a, maybe it's 0, maybe it's not, and 3. What happens due to this rate taking place between 0 and 3 or between whatever those numbers are. But x is a variable, whereas a is a parameter. It'd be a single number for every function. But what this tells us is the accumulation is happening at rate r sub f for every value t between a and x. So t is this kind of temporary variable that we use. It doesn't, if I were to come up with a way to express this without the integral sign, which we're going to learn how to do eventually, just not right now. We don't need to worry about that. We just need to be able to express the accumulation, not write it in a different form. But this a sub f of x is the accumulation of changes due to rate r sub f, where I measure all those rates of change between any starting point a and a general x in the future. So I can substitute in later a value of x and have this represent a value, but for now this represents a function. So I use every value between a and x, not just the beginning of every interval. If I imagine these intervals to be infinitesimally small, then every single point between a and x, a and any value of x, is going to be used. So I'm going to use not just like 7 or 8 rate values, I'm going to use all of them. As if I'm like able to pick grains of sand and put them on the line, I'm using every single y value of that rate of change function that there is. Using all of those rates times a little bit of time. So this is my rate function evaluated at some spot times a little bit of variation in where that spot goes to. So I use, this is the equivalent of the width of my interval and the value of the rate at the left end of that interval. But when the intervals are infinitesimally narrow, then I've got a rate value times this infinitesimally small thing. I've got infinitely many of them, but essentially what I'm doing is all the rate values times a little bit of time added together. But just kind of like the filling up the Grand Canyon with sand, if I have enough little grains of sand, it will fill it up, and it doesn't have to be infinitely big or infinitely small. It's the weird mathematics of infinity that makes this work out okay in the end. So if I want to know not just how much has accumulated between time 0 and time 3, or time 0 and time x, or time 17 and time x, whatever it is, if it's not just between 2 points in time, if I want to know how much of something there is altogether, including however much I might have started with, but maybe before the rate function applied. So this example, this function picture that I have up here related to sand on a scale. We were pouring it on at this certain rate, but before we started, there could potentially have been already sand on the scale that wasn't poured on at any known rate, it was just there. So if I want to know not how much sand has been put on the scale since time 0 was the time A in that problem, but how much sand is there altogether, I have to account for how much there was at time 0. So I could write this a couple of ways. I could just use a symbol to represent how much we started with. I could call this P, and it was in hundreds of pounds of sand. So P 100 pounds of sand plus whatever happened due to the rate. But this P here is also the same as, well, if F is representative of the total amount of sand at time X, and this story was starting at time 0, that was the sand story. Starting at time 0, there were P 100 pounds of sand. Well, then F of 0 would be the same as P. So F of X could be F of 0 plus something else. That sounds kind of like a circular definition, but you can know something about a value of a function apart from what its function rule is. So I could say something to define f of x, including some f of 0, and just use that, just as I use p, as just a symbol to represent a starting value. But f of 0 would tell me what that is. That would tell me, oh, that's the amount at time 0, plus what happened after time 0. So in any case, generally speaking, we talked about this before your test, I know, but I just want to repeat this, how these have the same bits and parts in them. When our delta x is extremely small, there's not any difference between the sum terms, the full intervals, and the current term, that partial interval, because there's no such thing as a partial interval when you've made the intervals as small as imaginably possible. So these are all the same size, so I'm just going to represent them all as the sum. So just, we'll just keep that all in there. So thinking about just matching up the parts above and below, it's not an exact match. They represent slightly different things, but essentially the same. Just like on this integral sign, I've got a bottom number and a top number. On this summation, I've got a bottom number and a top number. That tells me where I start and stop. Now, these are counting numbers of intervals. These are actually talking about x values or independent variable values. But again, it's a starting and stopping point. It tells us where to start, and well, in both cases, that stopping point involves the symbol x, so these are actually functions, not specific spots to stop. And we talked about this, but this rate function is shown in both places. And this summation here, I could call this r, or I could call it r sub f. We've talked about that a few times, because the rate at the left end of intervals, the exact rate at the left end of intervals, is equivalent to the approximate rate at the left end of intervals. So I could even use r sub f in both places. Now, the left side, the name of this function, a of x versus a sub f of x, just that subscript difference is the same as we did for anything else. It's the difference between approximate and exact. So this represents an approximate net accumulation between a and x, the starting point and the ending point. When j equals 1, this turns into just the value r of a times delta x. And we're starting here at a. And we're summing. And again, like this is our Greek sigma, indicating sum, and this is a Germanic s stylized, also representing sum, adding up things. The accumulation is a mdx sort of expression, a rate, times the amount of time that I use that rate for. So this big ugly expression, the rate at the left end of an interval, times delta x, versus r sub f of t, the rate somewhere, times a little bit of time. And you can even think of it as like literally time, like seconds or something if you want to, if that helps you remember what this is, like rate times time. But it doesn't have to be time as the independent variable. And this use of the letter t is just to distinguish it from x. So x and t have different roles here. T takes on all the values between a and x, so it can't be the same, it can't also be an x. Just the same way that j lets us talk about all the different intervals between a and x. Here, t lets us think about all the different spots between a and x. So I didn't want to use x here either, same sort of reason. So the starting value is a in both cases, or in other words, when we're measuring net accumulation, it has to be between 2 points in time, so it has to have a starting point, which we always use this lowercase a, and an ending point, whether it's a number or an x, so that I have an accumulation function as opposed to an accumulation value. These are written in function format, but if I wanted a sub f of 17, I put a 17 there, I put a 17 here, and that would give me exact accumulation. If I put a of 17, and I put 17 here, that would give me approximate accumulation. But the x value can either be an x when we're writing a function rule, or it can be a number if I want to know an amount of accumulation between a and that number. So this is a function, a sub f of x equals this integral from a to x of r sub f of t times dt, or this accumulation due to rate r sub f, where our independent variable is measured taking on all the values between a and x. So looks a little bit weird. A, there's a whole bunch of letters in it. B, other than multiplication, there's not a whole lot of operations there. It doesn't tell us actually how to get this done. Like, so how do I do that? How do I get a value for this? So something like g of x is sine of 3x, or h of x is this quadratic function, or even messy things with square roots and logarithms. This last one, like if I asked you to find c of 10, you would not do it by hand. You could either write it out as like square root of natural log of 10 minus 2 over e to the 100 power, something like that. But just like this last one, it's like, well, I can write out an expression with slightly more information in it, but I'm not really going to try to estimate that. But you know that e to some power, well, e is 2.7. If I raise it to 100 power, it's a huge number. And then there's this division of the square root of, I don't know, natural log of, what did I say, 10? is maybe 2 or 3, and then minus 2, it's a small number, take the square root and say, oh, well, this is going to be some small number if I do C of 10, because I've got a small number on top and a huge number on the bottom. You could maybe estimate a value like that. Now, this, first of all, is kind of vague because it doesn't have an actual rate function in there. It just has r sub f. But even if I put an actual rate function in there, like let's say I said, let's see, 7x cubed or 7t cubed dt. It doesn't really tell us what to do with that. It's like, oh, well, it's the rate is 7x cubed. So if you wanted to find a value for it, the estimating you would be doing would be exactly what we were doing before. Thinking about, okay, what are the rates? And let's say I'm going to use each one for a little bit. I'm going to add them all up. And so this notation, although it's nice because it's succinct, it doesn't actually tell you what would need to be done to get an approximation. Now, that said, if you want to evaluate, let me just define C, let's see, what is it? Control 9. C of x equals, but I have the square root of, there we go, natural log of x minus 2 all over e to the 10x. Oop, not that much over. E to the power 10x. So if I wanted to know a value for C of 10, yep, extremely small, 2 point something times 10 to the negative 44th power. Okay, as expected. But despite the fact that it's not any more maybe decisive, GC knows what this integral is. So let's say, let me define, I'm just going to call it R and not try to type in subscripts. Let's say that I have R of, oops, control 9, there we go, R of x. My rate function is, I don't know, 7x to the 5th power minus 3x cubed, oops, minus 3x cubed plus 1. All right, so thinking about this right here, if I write in a function with r defined, if I write in this with a value of x, GC will actually calculate it. And what it's doing is precisely what we did with that sum, only with extremely, extremely, extremely small delta x's. It doesn't have to choose a delta x. It automatically knows if you write the integral sign, we're going to let delta x be approximately 0. So I'm going to define a of x just like that, only without the subscript because it's too hard to write. So control 9, good, equals. There is an integral that's built in here, this integral sign. I don't want it to be from 0 to 1. Let's say it's from 0 to, I don't know, 7 or something. And I say, now, oh, let's see. I actually want this to be an x. And actually, so there's, in this, you have to be very careful because it automatically puts x's in places, and you don't want to have x's in 2 different sorts of places. So I have r defined above. So now it looks just kind of like this, only I'm not going to define a as a parameter. I'll just use 0. But this is just defining a function. Just like my line above was defining what r was, this is defining what a is. But if I say calculate a of 10, it has a value for that. Because it knows what this integral is, just like if you've been paying attention, just like you know what this integral is. It means the amount of accumulation between 0 and x, so I've just said 0 and 10, due to this rate function. Now thinking about this rate function, this is an odd degree polynomial. It does have a minus sign in there. If I put a plus, it'd maybe be more obvious. But if you graph this r of x function, it's all positive rates in the first quadrant. At least past a little tiny bit, because it starts up at 1, and it go, other than between 0 and 1, it's going up, or 0 and like 7 somethings, some weird small fraction. But it's going up into the first quadrant. It's got all positive values, and a 5th degree polynomial, especially with a 7 coefficient, is going to have extremely large positive values by the time I get to anywhere close to 10. So I've got extremely large positive rates, and I'm measuring what happens between 0 and 10. Well, there's going to be a lot that happens. It's going to be a lot of positive accumulation. I don't even know what this number is. Let's see, 1,159,176.7. But this integral function isn't just some mystery sign that you have to do something else with. Just kind of like the function at the top with the natural logs and the square roots and the e's. That's maybe a little bit easier to mentally process, like, is this a large number or is it a small number? I don't really want to do this by hand and make a numerical estimate, but I'll get large number or small number out of it. Same thing with this integral sign. It's really tedious to get a numerical value mentally. But I say, well, if I think about the fact that this is this odd degree polynomial, it's all going up in the first quadrant, so that's all positive and really large positive rates, this should be a large positive answer. Same sort of way. And so it's a weird looking function, but it's not really any worse realistically than a lot of other functions that you have used. It's just that those others specifically state what operations and functions we're using. Like, okay, we're doing natural log of something, and natural logs are kind of everybody's least favorite mentally estimate them sorts of things. And e to a power, it's like not something to do by hand. But nor is taking a polynomial like this and finding its value in maybe like 100 or 200 different places and multiplying and adding them together. But this notation literally means to do that. Well, not just 100 or 1,000 places, but infinitely many places in reality, essentially. Take each value of this, multiply it by a little bit of usage, and add all of those together. So this notation with the integral sign, it seems kind of like it's missing something, like it's not telling us what to do. It's just that you have to understand the notation to know what it's meaning for you to do. So it's what's called an open form expression or an open form function, in that it doesn't explicitly state all of the pieces that you need together, but it's not really any worse than a lot of things that you have seen before in terms of you don't want to do it by hand necessarily, or this isn't easy to process. But there are some ways in which we'll talk about how to do it, like in like 3 or 4 weeks. We'll be dealing with how would I do this with an actual R function written in there, like that polynomial function. There are ways to get to those answers without using just computer programs. It takes a little bit of trickery and what we're going to learn between now and a few weeks from now. But it's not just a simple like, oh, well, since it says this, I'm going to add 3 and divide by 17 and put in x and then we're done. You can maybe estimate this at this point numerically, but so can GC. So you can just pop it in GC. It's just as good. And lots of calculators can do a numerical integral. The ones with a function with an x still in them, this isn't something to calculate, but this is something that is literally defining a function already. So it's not that you're only partway done. This is a legal definition of a function, but it describes how that function is created. I'm using this rate between a given starting point and x. What happens because of it? The sum of all of the mdx's, the sum of all the rate times time, if you want. So it's kind of a conceptual description of what's going on, but it doesn't actually help you get numerical values very easily. Closed form functions, like polynomials, some of them are pretty easy, relatively speaking. You probably didn't think so the first time you saw them, to find values for, because it shows you all of the operations that you need to do. And there are more advanced operations than squaring and multiplication and adding and subtracting, which is why in reality they're not necessarily much easier to deal with. But the ones at the top certainly look a little bit odder because they don't necessarily, even if I have a rate function here, there's not a simple way to get an exact answer to that. So it's, in a sense, it's a little bit frustrating, but just realize that something written in this form can be an exact representation of the accumulation without you being forced to do the computations to find out an amount. So let's see if I can make this any. I'm going to get out of this screen and just make this bigger because that's a little bit too small. Nope. Why won't it go away? It's a little bit better. All right, so I'll scroll up so we can see more questions. But this a tub has a clogged drain that still lets some water through. We've done this sort of thing. I think it was a sink last time. At t equals 0 minutes, the faucet's turned on. And the graph here shows the rate of change of the volume of the water in the tub. So this is not the amount of water, this is the rate function that's pictured. So there are a few questions visible right now. Question A, at what time does the tub have the most water in it? Question B, at what time does the tub have the least water in it, between time 0 and 7? And is there more or less water at t equals 7 minutes than when the faucet was first turned on? So think about this graph. Again, keep in mind this is a rate graph where we're looking at a picture of the rate of change of the amount of water in the tub given in gallons per minute. And we have a tub that's had a clogged drain and the faucet was turned on. So think about what's happening to the amount of water in the tub for the first 7 minutes and then think about those 3 questions. I'll give you a few minutes to think about these and see if you can answer those 3 questions with your neighbors. All right, so before we get to those questions, let me ask this question. So at the very beginning, I see this blue curve seems to go through 0, 2, and then go downward from there. So the point 0, 2, what does that mean? Like, what does this spot mean about the water in the tub? What's going on around here? What's the 2 have to do with anything? Is that how much water there is in the tub? Is that how fast the water's leaving the tub? Is that how fast the water's going into the tub? What is this 2? What are the units on it? Yeah, this is gallons per minute. So I've got this 0, 2 point on the graph, which means at time 0 minutes after turning on the faucet, the water's going into the tub. The change is a positive 2 gallons per minute. Since it's positive, that would indicate more gallons, right? So the water is building up in the tub. Now, I don't know how much there was to start with. That isn't something we were told. But when I turn on the faucet, the amount of water in the tub is initially increasing at 2 gallons per minute. So this graph goes downward from there. What does that indicate about the rate of change of the volume of the water in the tub? It was 2. Like by the time we're a little over 2 minutes into this, I'll just call it 2 minutes in, it's about at 1. So at 2 minutes into this, having turned on the faucet, is there more or less water in the tub than there was at the beginning? More, right? So I've got a positive rate of change of the volume of water in the tub. So all through here, the volume is increasing, but what is the going downhill about this? What is it that's decreasing? The rate, yeah, the rate at which the rate at which the volume is increasing is becoming smaller. So it was increasing by 2 gallons per minute, but now it's only increasing by 1 gallon per minute. It didn't increase by 2 gallons per minute for a whole minute or 2 minutes or anything like that. That's just around here. That rate was decreasing all along, but it's a positive rate, meaning the volume is increasing. The volume's increasing at a rate of around 1 gallon per minute by the time 2 minutes have elapsed. So if I wanted to estimate how much water went into the tub over the first couple of minutes, say, well, it was 2 gallons per minute, dropped to 1 gallon per minute, so let's say about 1.5 gallons per minute on average, something kind of vague like that. Or we could use our approximation technique, split this up into intervals, and say like, okay, well, over the first couple minutes, let's see, 2 gallons per minute for half a minute, and then, pick a few other values and use each one for a half a minute or something reasonably short, and figure out how much water went into the tub. But over the first couple of minutes, water definitely went into the tub. By what point in time was the tub the fullest? When did it have the most water in it? Question A. Yeah, a little bit after 4, right here. By this point in time, maybe that's 4.25 minutes. The tub has the most water in it, which maybe seems weird because that's when this graph hits 0. But this graph, the rate graph hitting 0, and specifically the fact that it was a positive rate and then became a negative rate, indicates that, well, the tub was getting fuller, between these 2 times. But between time 0 and time 4.25, the tub was getting fuller because we've got positive rates. And then after that, that's when the rates become negative up through, well, we just stopped at 7. That's the last time we have information. The tub is emptying between time 4.25 and, well, 7 when we stopped having any data here. So it's not that there isn't water going in. The faucet's still running, but it's just that there's more water going out than going in. So net change-wise, we're losing water in the tub. So the tub was fullest by just after 4 minutes. And then it became less full after that because the rate of change of the volume of the water in the tub was negative. So we're losing, not much, but 1/4 gallon per minute, maybe 1/2 gallon per minute, 3/4 gallon per minute at these various points in time. So thinking about B and C then, these other questions. At what time does the tub have the least water in it? And is there more or less at time 7 than at time 0? Which maybe those are related questions. Well, just based on what we're talking about, do you think there's more water at time 7 or less water at time 7 than at the beginning? More. It was filling for quite a while, right? For the first 4.25 minutes, the tub, however much water was in at the beginning. Maybe it was an empty tub, maybe it wasn't. There was water going in for 4 and something minutes at rates as high as 2 gallons per minute. And then for the last couple of minutes, 2 3/4 of a minute or so, it was getting less, the amount of water was decreasing, but it wasn't decreasing very quickly. It was decreasing by values that weren't even as low as -1 gallon per minute. So lower rates of decrease than there were rates of increase earlier on. So by the end, I've lost a little bit of water through these last few minutes here, but not as much as I gained during the first 4. So seems like, yeah, more or less water at time 7. There should be more water at time 7 than at the beginning. There's the most at time 4 and a quarter, like this spot right here. That's when there's the most water. When was there the least water? Time 0. Yeah. So just use this. So however much there was, it could have been 0 water in the tub, maybe an empty tub. Maybe it wasn't. Doesn't really matter. We've got more water going in for these first 4 and a bit minutes, and then water going out for the next 2 or so minutes. But you can maybe see from the relative sizes of the positive rates as compared to the negative rates, it didn't go out nearly as quickly as it went in, or the water wasn't decreasing as quickly or as much as it increased during those first amount of times. And you can kind of see that from the size of these, just visually estimating. But if you did any sort of estimates with the rates like we did last time, you'd have very close to 0 negative rates versus not as close to 0 positive rates, and also for more intervals. All right, so moving on from those kind of calculation type questions, think about, where's this? There we go. All right, so I'll leave this picture on there so you can still imagine the picture. But suppose that the rate of change of the volume of water shown is, and we have this formula here, R sub V of t equals 0.03 t squared minus 0.6 t plus 2. So now we could have specific values if you wanted. You could find out where that 0 is, whatever you want to do. And also let's say that the tub started with 2.5 gallons of water in it. So at time 0 it started with 2.5 gallons of water. Not that this is supposed to be 2.5, this is still our rate. You can see at time 0 this rate would be equal to 2. That actually matches this function here. So there's actually 2 questions here. I want you to try to write an integral function that gives the accumulated change in volume between time 0 and time t. Let me just use that as time x, because that's, whatever, doesn't matter. We'll talk about the letters. The letters sometimes make it confusing. And then write an integral function that gives the total volume of water at time t. So I want 2 different functions. One that tells me how much water has gone into the tub since time 0, and one that tells me how much total water there is by any time t since time 0. So that's a sub v and v. And they're both going to be written not in nice kind of like polynomials and square roots and that sort of format, but just as integral expressions. And you can either use function rule for r, or you can just use the symbol for r also. The difference between those 2 parts has to do with this 2.5 gallons. So think about what we're talking with integral functions and how I express an accumulated amount and a total amount based on knowing the rate of accumulation. It's the shorter version of the big old integral, or the big old summation accumulation. As a hint, I'm going to need to use t on my integral sign if I want it to be a function of t, because I'm going to tell it where it ends. And it's not a mystery time a, we're starting at time 0. So think about what you could write inside the integral. You have to pick some letters of choice. But t's already been used, so you can't use t anymore. All right, so for this guy here, the accumulated volume between time 0 and time t, for any time t, and realistically speaking for this problem, I'd only want to use t values between 0 and 7. By the way, if you put 0 to 0, your answer is going to be 0 because nothing accumulates if you don't give it any time to accumulate. But the expression that I need here is essentially an MDX expression. I need an expression for my rate and an expression for like an extremely small, a differential change in that independent variable. And I can use whatever letter I want other than T or V or A. I have to use something else. I'll just use X, like MDX. But instead of using literally the symbol M, I'm going to use this. So I could write R sub V of X dx. I can't use t because t already has a meaning here. T is my independent variable. And inside here, again, what I'm doing is letting x take on all the values from 0 through t. So I don't want to let t take on all the values from 0 through t because that's too many. T can't take on values up to itself. That doesn't quite make any sense. Or if I had t in two places, if I said a sub v of 7, that'd be an integral from 0 to 7 of r sub v of 7, d7, and that doesn't really make any sense. So this just needs to have a different letter. I could write it, instead of writing r sub v of x, I could write out all of this, but just use x's in it. So I'm going to do that so that it's not just a symbolic function, but so that it has all of the pieces we want. So I'm going to have 0.03 x squared minus 0.6x plus 2, and then dx. And because I have it written in this long form with multiple terms, just like in regular algebra, if I want it all to be multiplied by dx, parentheses. Sometimes if it's a very short function, you won't see those parentheses noted. It's just kind of assumed because, well, when you go to calculate this, you're not actually going to be doing a whole bunch of multiplication. But symbolically, this is actually multiplication that's going on. So I want to have those parentheses there just to make sure that I don't lose sight of the fact that all of this is multiplied by dx, not just the part closest to it. So here's one way I could write this. The other way would be to write r sub v of x, the symbols in that spot. And this represents the net accumulation. So the accumulation just due to this rate, summing up all the values where x takes on all the values from 0 to t for any value of t I want. This rate times a little bit of change in that independent variable, a little bit of change in x. I let x vary from 0 through t. If I want to know the total volume, the only difference is I need that, the tub started with 2.5 gallons in it, and then all the rest came from accumulation. So exact same as before, 0 to t, 0.03x squared, or you don't have to use x, you could use q or p or j or pick your favorite letter, just don't use t, again, for the same reason. We can't have it having two different meanings. But either of these functions would be well defined not only on a piece of paper, also in GC, and could be evaluated by GC. We will learn how to evaluate these like more manually, but just like lots of other, like the evaluating is like that's something that calculators can do, the evaluating. What they cannot do is put together this function. What needs to be computed, evaluated, how are the pieces connected together? So your brain power is needed to put together the functions. Evaluating functions, just like evaluating like square roots and stuff, please put it in a calculator. But if you need to write out a function, not a value, I need your brain power to put it together properly. So we're not going to focus on a lot of computation of numerical values for these, although it is possible to write out this into a series of steps where it is just annoying arithmetic. I don't want you actually spending your time doing annoying arithmetic because, hence the adjective annoying. It is just possible, but not what we need to spend our time on. So, all right. Anything else I want to talk about with this? Any questions you have related to the structure of these functions, this net accumulation and this total amount or total accumulation, which includes an initial value? So that by substituting in the first function here, if I substitute in t equals 4, I would have this almost largest value of accumulated water in the tub. This number would be 2.5 larger than that, meaning the total amount of water in the tub, but this would be the amount of water between time 0 and time 4 minutes that went in. If I said a sub v of 4 versus v of 4, they'd be 2.5 gallons different, one indicating how much went into the tub during 4 minutes, and the other indicating how much water there is in the tub by time t equals 4 minutes. All right, so let me clear this off so this doesn't turn into a mess. All right, so what I've got here are 6 different integral expressions. Some maybe could define an amount of accumulation. There aren't any that have any initial value added onto them. They're not named anything right now, but look at the structure of each one and see if it seems like it could be representing a net accumulation between 2 points, between a time a, which might be a number, and a time x, or see if it's an amount of accumulation between 2 values, if there's all numbers on the integral sign, or if there's something wrong with the way that it's written so it isn't very well defined. So, for instance, this first one here looks pretty nice. I've got g of t dt, so this is a rate time, like an mdx sort of expression, so that's a good start. And on the integral sign, I have 4 and x. So this would measure accumulation between time 4 and any general time x, where I let t take on all the values from 4 to x. So this looks good. Maybe I'd call this a sub, I don't know, f of x. This would be a function of x, where I get to sub in different values of x to get different values of accumulation. And the rate here is g. So this is some rate function. Where I let t take on all the values between 4 and x. So that seems good. Now, in contrast, let me find, here's one that looks kind of similar. It's got, instead of having a generic rate function, it has a rate function rule. So I've got sine of e to the t times dt, so far so good. I've got our mdx sort of expression between time 0 and time t. Here's the problem. So this is a sub f of x because I get to choose this endpoint here, x. If I call this a sub, I'll just call it something else, I'll just call it a sub f of t, so that I get to choose this endpoint here. If I said find a sub f of 4, you'd have to put in a 4 not only there, but also there. So it wouldn't be a varying rate, it would be a single value for the rate. And then how do I let 4 vary from 0 to 4? There's too many t's in this one. So what I would need to do to fix this, to make it something better, is to choose a different value for this up here. So if I were to change this and make it a sub f of x, and put an x in that spot instead, then it would be perfectly okay, other than I need a parenthesis there. So look through the rest of these. There are a couple of these that are just not functions, they're just values. See if you can determine of the remaining 4 which ones are just a numerical value, and if any of the others remaining are okay, or how you could fix them up, like I did with the last one, to be net accumulation functions. for instance, this top right one. Is this okay as it is as an accumulation function, or do we need to fix something? Fix something. Yeah, same as the last one. I've got x overused here. I can't have x be varying from -3 through x. That doesn't quite work out. We need a different letter, and you can replace whichever one you'd like. Let me change the different color here. There's nothing magical about you have to have t here and you have to have x there or anything. You can do whatever you want, but let's not have x here. Let's have, I don't know, q. Like I said, you can make whatever letter you want, but this top, if it's a letter, a symbol on the top there, that's your independent variable of your function in reality. So I could call this a sub h, I guess, since this is r sub h, the rate of change of h. I'll talk about the accumulation in h between -3 and q, apparently. And then I could substitute in different values for q and use my rate over different intervals. All those intervals apparently starting at -3. What about this one here? Is this okay, or does it need fixing? Let's see. I have a rate function involving, I think that's a v, maybe it's a nu, who knows. But got this v-looking symbol here, and I let v take on all the values from a through x. That's okay. It's kind of a parameter a, but that's good. So I could talk about this as an accumulation function in, I don't know, some mystery function f. If this is r sub f of v, the rate of change of function f, then this whole thing is the accumulation, net accumulation for function f between a and x, making it a sub f of x, where this a is kind of an understood part of what net accumulation we're computing. Now these last two that are remaining, there's not really any problem with them, but they aren't functions. They're both representative of numerical values. If you put this into GC, it would give you a number. This is equal to one number. This is equal to one number. Don't know what it is off the top of my head at all, but these are, well, this one has this a times a sine function of e to the a power, and I let a take on all the values from 10 to 15. Whatever that turns into, it turns into. Same here, I've got cosine of x plus x cubed as my rate function that I multiply by dx, and let x take on all the values from 0 to 8. Okay? But that's not an accumulation function, it's an accumulation amount. So I could call this something like a of 8, the accumulation between starting point 0 and 8. I could call this a of 15, accumulation starting at 10, or the accumulation up through 15, or since 10. So just like in these others, the starting point of the accumulation is something that's understood or described as a part of the question. We didn't use these when we were writing the notation for the, like the left side, the naming these. But there's a way to kind of fix that problem. And that's, instead of talking about just the net accumulation, I could talk about how this is related to the total amount function. So for instance, this is a total amount of accumulation in function. I decided that the rate is r sub f. So f is this total amount of something, how much sand I have on the scale altogether. Whereas a sub f is just how much sand has accumulated since time lowercase a. Well, if I said that f is a function that describes the amount of sand at any time, so f of x is the amount of sand at time x, if I wanted to express this, the accumulation, the amount of sand that I've gained since time a, or by time x, that'd just be f of x minus f of a, right? How much has accumulated between time a and time x, how much more or less I have. This could have positive or negative values. Pop it in GC and see what its value is for different values of x. But if I want to know how much change there is, net change between time a and time x, time being the input, final minus initial. Same here. This is accumulation by time 15 based on like, well, measuring since time 10, that's a little bit confusing. Let me call this a sub f, so I have an underlying function that this is measuring a net accumulations in. Say, oh, well, this is the net change between time 10 and time 15. If I call this r sub f of apparently a, then f is the total amount function, how much of something I have, or the total accumulation, not just net accumulation between 2 points in time, where the start has to be defined. I can say, oh, well, this is just the total amount at 15 compared to the total amount at time 10, that net change, final minus initial. Same thing here. I say, oh, well, this was now f of x minus f of 0. F of 0 doesn't have to be 0, so depending on what this f is, this amount whose accumulation was measured here, I could do that not just for the ones that have more numbers involved, but for any of these. I could call this, let's see, h. h of q minus h of negative 3. The net change is final minus initial. And so if the underlying function, that subscript function, is called h, in the rate function and in the net accumulation function, I could just use h itself, final minus initial, also to express that. Now, do I have a formula for this? No. So is this more meaningful? Not really, but they are equivalent. This would be a different way to express it. I could call this a sub h of q, or I could call it h of q minus h of negative 3. That kind of incorporates that negative 3 into the symbols instead of it having to be understood about this capital A function. So let me clear off some space here and just write something in general about this. So if I have, I'm just going to write this in the middle. If I have a function r sub, well, let me just write on a blank document then, or something. I don't know what's going to open up when I open this. Come on. All right. So if I have a rate function, r sub f of x, the f here is a subscript, meant that this is the rate of change of f. Or it measures how the function f changes as x varies. A sub f of x is a net accumulation function. And with this subscript here, it's an exact net accumulation function. But there's infinitely many different net accumulation functions we could write, depending on what starting point we want to measure relative to. So all of them could be written something like a through x for some value of a. So we get to choose it based on, depending on what we want to do. But to get this to be a sub f of x, I'm going to write r sub f of something that isn't x times d same something. So r sub f of t dt. So m dx sort of expression measured from a through x. If I want to talk about the exact total accumulation or the exact total amount, I called it f of x. But this exact total accumulation, you'll see both of these phrases, and sometimes total accumulation sounds weird. So I'll say exact total amount. Well, in terms of how these two are related, this expression here is the same as f of x minus f of a. So if I want to know, well, f of x then is just this integral plus f of a, just thinking like algebra equation here. How do I solve for f of x? Move this to the other side, right? So f of x can be expressed as f of a plus the accumulation that happens after point A due to our rate function. And this is one of two different forms of what's called the fundamental theorem of calculus. It relates our rate function to our accumulation function, not just between 2 points, but just general total amount. But all this is y final equals y initial plus mdx. But this guy here, for any value of a that you choose that's within the domain of function f, for any value of a that you choose, this is going to be a true statement. So if I know a rate of change for a function f and any value of that function, I can write a formula for it. Now, this might sound like, okay, if I have a constant rate of change sort of function, if I have a linear function, this is just point slope form. Y value plus m times x minus x1 dx, whatever. So one of the questions on your test was something about, I don't know, building tables, and it was kind of a piece by piece sort of expression. I'm going to borrow some space at the top of this sheet here, rather than erasing the bottom part. But if you have a constant rate of change, instead of having r sub f of x being a whole formula, let's say r sub f of x was 7. And I know that f of 2 is 9. That is, graph-wise, I have a point at 2, 9, and I have a slope of 7. Okay, well then writing an equation for f of x from this, sorry, I didn't label it, that's my point, 2, 9. Oh, just y initial plus my rate, 7, times however far I've gone past my initial x value of 2. And that's how we wrote our piecewise functions, that's how we did point slope form, and there's a question about building tables on your test, same sort of thing. Now, if r is not a constant, you can't do this mdx quite so simply, but it's just this. I've got a rate function times dt instead of this expression. This was our m dx sort of expression. This is a m, this is a, well, not dx, but dt, same thing, it's a differential. And I just add up, instead of having one rate to use for any interval, I have a formula for all the different rates that I'm going to use, and I'm going to use all of them for infinitely small amounts of time over entirely an interval that starts at a and ends at x. And x doesn't have to be a number, just like this x doesn't have to be a number. I can sub in a number later to get a value. But this is the algebra 1, algebra 2 version of that. I've got a point and a slope, write an equation of a line. If I want to write an equation for a function, I need one value of that function and its rate of change function. So we're just extending what we learned from algebra and extending it to situations where we have not a single rate, but it's the same general structure, and that's how all of our pieces are related. We have a rate function, which we can imagine turning into an accumulation with a starting and stopping point, starting at some particular point A and going onward from there. But if you want to know the total amount, you have to know how much of whatever it is you started with at the beginning when you started measuring your accumulation, because it doesn't always start from 0. Like sand on a scale maybe starts from 0 at some point in time, but if you didn't know the rate for a while, you have to start with an amount that begins when your known rate function begins. But this fundamental theorem of calculus, then, it has two versions to it. One has more numbers in it, but it's really just the same thing rearranged with, instead of having an x here, it has like a b there instead. It's more like this form here. So the other portion of fundamental theorem of calculus, if you look it up, usually it says like part 1 and part 2, and depending on which book it is, they switch which is which. The only difference between these two start items here and what you'll see typically in a book if you look up fundamental theorem of calculus is, oops, let me erase. There. For one of these parts, they'll have it generally as two numbers. So this is an amount of change between 2 points. It's final minus initial. But then this part is written as if it's completely something different. All it is just really rearranging. So whether I have an x there or a b representing, instead of a function representing some second parameter and ending point to the accumulation, these are the two halves to what's called the fundamental theorem of calculus. If I know a rate, I can find how much accumulates between any 2 points. And if I know a rate, I can generate a function for a total amount of accumulation, as long as I know one value for that total amount at some point in time in the domain. So, but like I said, these are really just algebraically rearranged versions of the same thing with just an alteration from using an x to using a b, a parameter for a specific ending value instead of a x indicating a function that can be substituted into later. But they're used essentially the same. So I'll stop at that for today. What we're going to talk about on Thursday is, well, the other way around about this. We're going to talk about, so what if I know f? How do I find the rate function from that? How do I estimate a rate function based on knowing an amount of accumulation? Which, unlike when we started doing the other way around a month ago or so, algebraically, this is pretty simple. So we'll get through all this in like 3/4 of a class period. All right, so I will see you on Thursday.